Hello friends, welcome to the course Exploratory Data Analysis for Data Science with R software. So you can recall that in the last two lectures we had discussed the concept of movements, and we had also learned how we can compute them in the R software. And we also discussed that usually we are interested in the first four movements. Why? Because the first movement, particularly the raw movement, this is going to give us some idea about the central tendency of the data. The second central movement is going to give us the idea about the variation in the data. And what third and fourth movements are going to give us the information, we are going to discuss in this lecture. So we are going to understand here the concept of skewness and kurtosis, right? And then we will try to see what are the different measures to measure the properties of skewness and kurtosis of the data and how we can compute them in the R software. So let us begin this lecture and try to understand what are these skewness and kurtosis. So first we try to understand what is the meaning of skewness, S-K-E-W-N-E-S-S. The literal meaning of skewness is lack of symmetry, right? Now this skewness gives us an idea about the shape of the curve which is obtained by the frequency distribution, or say equally the frequency curve of the data, and gives us the information on the nature and concentration of the observations towards either higher or low values of the variable. So once we are trying to understand what is lack of symmetry, that means we need to first define what is a symmetry. When we are talking about the concept of symmetry in the data, then if I say that suppose my frequency curve is coming out to be here like this, right? So now if I say here, if I take here this line in the middle, so you can see here that the data on this side of this line and data on the right hand side of this line, that is distributed in such a way such that the structure of the curve here and here, that is the symmetry. So this is what we mean by the concept of symmetric in the context of this data. So now if there is a lack of symmetry, that means the data can deviate either on left hand side or right hand side of this line to have more or less concentration. So let us try to understand it, right? And if you try to see here, when I am defining here the concept of symmetric curve, which is here in this picture, let me give it here a number, figure 1, figure 2, and here this figure 3. So in figure 3, I am giving you here the idea of the symmetric curve of the concept of symmetric curve. So if you can see here, the shape of this curve here is like a bell. You have seen the bells like this one, and then there is like this one, right? So this structure of the bell, this is here what we mean by symmetric structure, right? So now we say that a distribution is skewed if the frequency curve of the distribution is not a bell shaped. So this is here a bell shaped curve, right? And the curve is symmetric. So when it is not bell shaped, then we call it as skewed. So in this case, what will happen? The curve will be stressed more to one side of the data in comparison to the other side. For example, if you try to see here in the figure number here 1, the data here is more on this side, on the left hand side, and data tapers off to 0 in the right hand side. And similarly in the figure 2, you can see here that the data is increasing gradually, and suddenly the data is more concentrated on the right hand side, right? Now how these things are happening in real life? For example, if I try to see the number of people crossing a particular point where there is a school. So suppose the time of the school is say morning 8 a.m. till say this 2 p.m. So now if you try to plot here the data, say from here say 6 a.m. to here, so suppose up to here, say here 12 p.m. So you will see that usually you have observed that if you try to see the traffic movement around a school, so at 6 a.m. usually the traffic will be very, very low, and suddenly just before the 8 o'clock, right, this traffic will become very high, right. Lots of students, their parents and different types of vehicles, they will be coming there, and this frequency and if I say here, the total number of persons who are crossing that particular point, this will very sharply starts increasing after 7 a.m. and then just before the 8 a.m., say up to 10 minutes before, 5 minutes before, this frequency will be very high, right, up to this point. And after this, say after 8 a.m., this people will start leaving this place, and then not many people will be coming to that point, say up to 12 p.m. So the traffic will be very, very low. But suddenly, say after, say here, if I try to say after 12 p.m. what happens? That usually, yeah, some traffic may be there, but if you can imagine a school which is isolated and not located on a main road of the city. So then what will happen here? If you try to look into the figure number 2, and if you try to see the traffic around 12 p.m. will be very, very less, and suppose the school ends at 2 p.m. So then you will see here that gradually people will start coming to the school to pick up their children, or some vehicles will be coming there, and gradually the traffic will start increasing and at about 2 p.m. the traffic is going to be maximum, and then suddenly after 2 p.m. around at 3 p.m. or say by 2:30 or 3 o'clock, this traffic will become drastically low. So you can see here that if you try to represent such a situation through this graphic, then the data say in the area of 6 a.m. to say 9 a.m. is more stressed on the left hand side than the data in the area of 9 to 12 p.m. in the figure 1. And similarly in the figure 2, the data between 12 p.m. and 2 p.m. this is very less in comparison to the data between say this 2 p.m. to 3 p.m. Right. So in this case, this frequency distribution is actually skewed, right. Whereas if you try to consider the same situation in the figure number 3, then around the central value, if you try to see, this data is almost has the same structure, right. So the frequency gradually increases, they reach to the maximum, and exactly with the same rate the data decreases, right. So, and yeah, one good example of such a bell-shaped curve is that you possibly have seen at your home, that when some food is cooked and suppose in the curry you have to add some salt. So if you try to take here on the x-axis the amount of salt, and on the y-axis you try to taste the taste. Well, this is a qualitative variable. I'm just trying to give you here the idea that how the things happen. So suppose the curry has no salt, then the taste will ideally be 0. Yeah, if you like salt, then gradually if you try to increase the quantity in the quantity of salt in the curry, then what will happen? That the taste will increase, and gradually it will increase up to an optimum level, where the taste is going to be the maximum, and after that if you add more salt, then the taste will get spoiled, and finally the taste will become too bad, right. It is something like this. So now we have to define how are we going to identify this data curve when the data is stressed either on the left hand side or right hand side more, right. So then we say that the frequency distribution for which the curve has longer tail towards the right hand side, this is called as positively skewed. You can see here, this is here the tail. So this tail is much longer than on the left hand side of the data point, and so we call this as a positively skewed curve. And similarly, if the data curve has longer tail toward the left hand side, so you can see here in this case, for example, this is much longer than on the right hand side, then we call that the curve is negatively skewed. And in the case of symmetric curve, there is zero skewness, there is no skewness, right. So this is how we try to define the skewness on the left hand side, right hand side, or we call it as a positively skewed or negatively skewed. So you can see here in this case, the figure 1 was positively skewed and figure 2 was negatively skewed. Right. Now, the question here is this: how do you define here a curve of symmetry? Means, well, if I try to say here, this curve is also symmetric, this curve is also symmetric. So how would you like to compare with that there is a departure from symmetry? So in order to understand the magnitude of departure from symmetry, we use the concept from the normal probability. So in order to understand the concept of the symmetric behavior, we use the concept of the normal probability density function. Well, you are aware about this normal probability density function. It is denoted as normal mu sigma square, where mu is the mean parameter and sigma square is the variance, right. And the probability density function of this distribution is given by like this: fx is equal to 1 upon 2 pi sigma square raised to the power of 1 by 2, or say square root exponential of minus 1 upon 2 sigma square into x minus mu whole square, like this, where x lies between minus infinity and plus infinity. Mu and sigma square are the parameters. Mu indicates the mean and sigma square indicates the variance. Now, in case if you try to plot this curve, then you will see here the curve looks like here this thing. So which has got a bell shaped curve and it is symmetric around its mean. So the mean is somewhere here, right. So we consider whatsoever be the value of skewness in the normal curve as a standard value, and then we try to compare the departure from symmetry. Yes, that's a different thing. How are we going to define the skewness, or how are we going to measure it quantitatively? That I will try to tell you. So in this case, the skewness is considered to be as 0. And similarly, after this skewness, I will introduce you the concept of kurtosis. So we also assume that the kurtosis here is 0, and then we try to compare. But anyway, that I will talk later on. So we are going to measure the departure from symmetry, like in these two cases, by comparing them with the skewness in the normal distribution curve. So now we define here the coefficient of skewness. Now you will see we are going to use here the concepts of movements, right. So do you remember that we had defined the central movements by mu1 as first central movement, mu2 as second central movement, mu3 as third central movement, and so on, right. So we are going to define here the coefficient of skewness as mu3 square divided by mu2 cube, and this is indicated by the coefficient of skewness as beta 1. So mu2 is here the second central movement and mu3 here is the third central movement. So try to see what are we doing. We are trying to take the third central movement and we are squaring it, and then I am dividing it by the cube of second central movement, right. Similar to beta 1, there is one more coefficient of skewness that we use, which is actually here gamma 1, and it is defined as here as say plus minus say square root of beta 1. The reason being, if you try to see in this case of beta 1, the mu3 can be either positive or mu3 can be negative, whereas mu2 will always be greater than 0. But when we are trying to consider here the mu3 square, this is always going to be greater than 0, and mu2 since is already 0, so the value of beta 1 will always be greater than 0. So if there is a departure from the symmetry either on left hand side and right hand side, then this beta 1 coefficient will not give us the idea about the correction of the or the sign of the skewness, whether it is positive or negative. But beta 1 will give only us the measure of magnitude of this departure from symmetry, whereas gamma 1 is the positive is the square root of beta 1. So it can take positive and negative sign. So gamma 1 will also give us the information on the magnitude as well as signs as positive or negative. How? Let me try to first show you that this mu3, mu2, etc., they are based on the entire population. But now we are going to compute these quantities on the basis of sample. So how are we going to compute it? So I defined here the sample based coefficient of skewness. So beta 1 is defined here. You can see here, this is your sample based second, third moment whose square is taken, and this is here the sample based second moment whose cube is taken, right? And similarly, if you try to take here the gamma 1, which is based on sample values, I simply have to take here the square root of this beta 1s with sign. I have to see, right. So now how to interpret them? If the value of gamma 1 is in the population, if it is 0, that means the distribution is symmetric. And in the sample based also the same interpretation goes. If the value of gamma 1 based on the sample is 0, that means the distribution is symmetric. In case if the value of gamma 1 is greater than 0, this means the distribution is positively skewed. So the same thing is interpreted in the sample based quantity also. So if gamma 1s is greater than 0, this means the distribution is positively skewed. And similarly, if gamma 1 is negative, it means the distribution is negatively skewed in the population. So the same thing continues in the sample also, that if gamma 1s is less than 0, negative, it means the distribution is negatively skewed. So this is how we are going to interpret about the nature of the skewness from the coefficient of skewness, right. And in case if you try to see here, I will give you here one more idea which is very important. We had talked about it earlier in the lecture when I was trying to give you the details about box plot and violin plots. In the case of this symmetric distribution, this curve is symmetric. So in this case, the value of mean, median and mode, they will be equal and they will be lying at this place. So in a symmetric distribution, the mean, median and mode, they take the same value, and in this case the value of gamma 1 is 0. Now I take a more interesting case, that if you have a positively skewed curve. Now if you try to look at the positively skewed distribution, then in this case the mode will occur somewhere here, the median will somewhere here, and the mean is somewhere here, and these values are on the x axis, and in this case the gamma 1 is greater than 0. So if you try to look at the values of mean, median and mode, then what is happening? Mode has got the minimum value and mean has got the maximum value, and median lies between the values of mean and mode. So mode is less than median, less than mean. So in case if you try to recall your discussion on box plot, then we had the idea about this mean value, median value. So you can look into the difference between mean and median values and can try to understand whether the data is skewed or not. And similarly, if you try to take here the case of negatively skewed distribution, then in this case gamma 1 will be less than 0, but in this case if you try to see here, this will be just be reversed. Mean value will be somewhere here median will be in after this and mode will be after that. So, if you try to see here, if this is your here x axis, then the value of the mean is here the minimum and the value of the mode here is the maximum, and median lies between the two, which is just opposite to your this positively skewed curve. Right. So, now you can see here by looking at the values of mean and median also and mode also, you can actually judge that whether the distribution of the data is positively skewed or negatively skewed, right? And yeah, I have just prepared all these figures at one place so that you can very easily compare them. So, you can see here the mode here is here, which is taking the maximum value, but in the case of say positively skewed, this is taking the minimum value, and in the case of positively skewed, the mean is taking here the maximum value, and here the mean is taking here the minimum value, right. And in the case of median, median is lying between mode and mean in both the cases, positively and negatively skewed curves. Whereas, if the curve is symmetric, then mean, median, mode, they take the equal value. And that is the same story in the case of normal distribution. The parameter mu, that is the value of the mean, the value of the median, as well as the value of the mode, right. Okay. So, there is one more coefficient of skewness, which is defined here as which is sample based movement as like as here x bar minus x bar mode. That means you try to take the difference of x bar and x bar mode and divided by sigma x. So, this value will be actually lying between -3 and +3. And similarly, if you try to take here, there is one more measure, because x bar arithmetic mean minus mode is equal to 3 times arithmetic mean minus median. So, the same thing can be given here also. So, this is another measure of skewness, right. So, if this S coefficient comes out to be greater than 0, that means the frequency distribution is positively skewed. If S coefficient comes out to be less than 0, then the curve is negatively skewed, and if S comes out to be 0, that means the frequency distribution is symmetric, right. And there are some more variants of this coefficient of skewness, because now you can see that it is based on the median. Median is the second quartile, or it is the 50th percentile. So, the same thing have been obtained, that another variant of coefficient of skewness, which I call it as SQSK, is defined as Q3 minus Q2 minus Q2 minus Q1 divided by Q3 minus Q2 plus Q2 minus Q1. And one more alternative form is, it is based on the percentile, because this is based on quartiles. So, on the percentiles, if P90 is the 90th percentile, P50 is the 50th percentile, then P90 minus P50 minus P50 minus P10, P10 is the 10th percentile, divided by P90 minus P50 plus P50 minus P10. So, both these coefficients will lie between -1 and +1, right. So, this is all about the skewness. Now, we come to another aspect, which is about the kurtosis, Kurtosis. Please try to observe these three curves. Let me call it here, say curve number 1, curve number 2, and see here curve number 3. Now, you can see here all these three curves are symmetric around, see here, this value. But when all the curves are symmetric, then how they are differing? They are differing with respect to the hump of the curve. For example, you see in the curve number 1, the hump is here, curve number 2, the hump is here, and the curve number 3, the hump is here, right. So, kurtosis actually describes the peakedness or the flatness of a frequency curve. You can see here that this curve number 1 here is more flat than the curve number here 3, right. So, how to measure this property? So, the hump of this curve is compared with the normal distribution hump. So, as I told you that for example, this is the normal distribution as I just discussed about it. So, this curve is bell shaped, no issues, it is symmetric, no issues. But now if you try to see here around this point, this is here the hump. So, whatsoever value of this hump which is defined by the coefficient of Kurtosis, which we are going to define, based on that we say whatsoever be the hump of this curve, this will be called as mesokurtic. So, whatsoever be the hump of this normal distribution, this is called as here the mesokurtic. And the curve which has got the hump where the kurtosis is less than the kurtosis of the mesokurtic curve, this is called here as a platykurtic, which is given in the curve number 1. So, first we are trying to compare the curve number 1 and 2. So, in this case, if the hump of the curve is less than the hump of the mesokurtic curve, then it is called as platykurtic. And now, if I compare the curve number 2 and 3, so curve number 2 and 3, it is 3 number has the hump here and the normal distribution or the curve number 2 has hump here. So, if this hump or the kurtosis is more than the hump or the kurtosis of the normal distribution, that is mesokurtic, then it is called as leptokurtic. So, the kurtosis of the normal distribution is mesokurtic, and the kurtosis less than this is platykurtic, and the kurtosis more than the mesokurtic is leptokurtic. This is what we have to keep in mind, right. So, once again you can see here I have used here the concept from the normal distribution to define our standards. So, the shape of the hump, which is actually the middle part of the curve of the frequency distribution of the normal distribution, has been accepted as a standard, right. And this property of kurtosis, this examines the hump or flatness of the given frequency curve or distribution with respect to the hump or flatness of the normal distribution, which I just shown you, right. So, the curves with hump like of a normal distribution, they are called as mesokurtic, you can see here like this, and those curves which have got a greater peakedness or less flatness than that of the normal distribution curve, they are called as leptokurtic, you can see here. And those curves which have got here the less peakedness or greater flatness than of the normal distribution curve, they are called as platykurtic. So, you can see here this the platykurtic curve is here, right. So, now the next question is how to measure this kurtosis or peakedness numerically. So, for that we have the Karl-Pearson's coefficient of kurtosis, which is defined by here mu4 upon mu2 square. So, you can now recall here is that mu4 is the fourth central moment and mu2 is here the second central moment. So, now you can see here that mu4 is always greater than 0 and mu2 is always greater than 0. So, beta 2 will always be positive quantity. And then you can see here in measuring the kurtosis, we are using here the fourth central moment. And you can recall that when we define here this coefficient of skewness here, right, you can see here we have used here the third central moment mu3. And that is what exactly I told you, that we are using the first raw moment to measure about the central tendency, second moment about the variance. Yeah, third and fourth moment, they are helping us in giving us the idea about the symmetric behavior or the kurtosis of the frequency curve. This is what I told you earlier, right. So, this coefficient mu4 upon mu2 square is denoted by beta 2, and we also define here one more alternative coefficient by gamma 2, which is beta 2 minus 3, right. So, now how we take the decision between these two, right. So, for normal distribution, if you find the value of beta 2 comes out to be here 3 and the value of gamma 2 comes out to be here 0. So, now we can define the limits for leptokurtic, mesokurtic and platykurtic. So, for mesokurtic, first we understand the kurtosis in the case of mesokurtic distribution, because we are taking the hump from the normal distribution curve. So, we say that mesokurtic distribution will have the value of beta 2 as 3 and gamma 2 as 0. Now, this is here like this. Now, when you are trying to consider a curve which has got a more hump than the normal distribution, that is your here leptokurtic distribution. So, in this case beta 2 will be greater than 3 and gamma 2 will be greater than 0, which is here like this. And similarly, if you are trying to consider here a curve who has got a hump which is lower than the normal distribution, this is platykurtic. So, in this case we will take beta to be less than 3 and gamma to be less than 0, which is here like this. Right. And the same thing will continue for your sample based coefficients also, right. And there are some properties about this kurtosis. For example, beta 2 is greater than equal to 1, beta 2 is greater than beta 1. Beta 1 was the coefficient of skewness and beta 2 is greater than or equal to beta 1 plus 1. This is just for your information, right. So, the sample based coefficient of kurtosis will be simply you try to compute the fourth central movement based on the data, second central movement based on the data and square it. So, this will be here your here beta 2s and the gamma coefficient based on the sample will be simply beta 2s minus 3 indicated by gamma 2s. So, and the same interpretation will continue that for leptokurtic distribution on the basis of data, if you find that beta 2s is greater than 3 or gamma 2s is greater than 0, then we will call that the sample is coming from a leptokurtic distribution. And if you find beta 2s to be 3 and gamma 2s to be 0, then we say that the sample is coming from a mesokurtic distribution. And if beta 2s is less than 3 and gamma 2s is less than 0, then we say the sample is coming from a platykurtic distribution, right. Now, after understanding this concept of skewness as kurtosis, we come to the aspect that how are we going to compute them in the R software. So, we can use here the package movements that we had used earlier to compute the movements. So, I can install this package by using the command install that packages, then I can upload it using the command library. Now, the sample based coefficient of skewness is computed by the command Skewness, Skewness, and then you have to give here say here data vector x, and if there are no missing values, then you can give here na dot rm equal to false. If there are missing values, you can use here na dot rm equal to true. And if you want to compute the coefficient of kurtosis on the basis of the sample of data, then you have to use here the command kurtosis, Kurtosis, and inside the parenthesis you have to write the data vector x, and you have to use here na dot rm equal to false, in the sense that if there are some missing values, you can use here na dot rm equal to true, right. But before moving further, one very important aspect for you to keep in mind and remember, that in the R software, the coefficient of skewness is actually computed by gamma 1s, gamma coefficient, and the coefficient of kurtosis is computed by beta 2 coefficient. This is what you have to always keep in mind. Yeah, sometimes people say that okay, either it is beta 1, beta 2 or gamma 1 or gamma 2, right. So, I am writing it here again very clearly that it is very important to note that in the R software, the coefficient of skewness based on the sample of data is computed by this gamma 1 s, and sample based coefficient of kurtosis is computed on the basis of beta 2s, right. So, now similarly, if your data has got some missing values, then the data can be stored suppose in data vector x n a, and if you want to compute your coefficient of skewness based on this, then you have to use the command skewness with the data vector xna, and you have to use here the option na dot rm equal to true. And similarly, if you want to compute the coefficient of kurtosis, then you have to use here the option, the command here kurtosis, kurtosis with xna and with the option na dot rm equal to true. Right. Now, let me try to take an example to explain you how these values will come like. So, I take here the same example which I considered in the several times in the past, that there is a data set of 20 participants who have participated in a race, and their time to complete the race is recorded in seconds, and this data is recorded in a time data vector. Now, if I use here the command skewness over this time, this comes out to be here 0.50. So, that means the data is here positively skewed. And similarly, if you try to see here, the kurtosis comes out of this time data vector comes out to be here kurtosis time as 1.70. Now, if you try to see what did this actually mean, kurtosis is now, if you try to recall, this is based on beta 2s and skewness is based on gamma 1s, right? How you have taken the decision on beta 2? Beta 2, if is less than 3, then you call it as platykurtic, right? So, this is here a platykurtic, but coefficient of skewness is positive because this is based on gamma 1. So, this is positively skewed, so, right. And similarly, if you try to consider the same data set with missing values, and I suppose I'd say that the first two values get missing, which are reported as na. So, I try to create the data vector here time dot na, and I write here these two values as na, and then I use the same command here skewness time dot na, and then na dot rm equal to true, and this value comes out to be here like his minus 0.06. So, you can see here, although the value is quite close to 0, but still it is in the minus sign. So, I have to say here that this is a negatively skewed data, because now you have removed two data sets. And kurtosis, if you try to see here, this is again 1.81, which is less than 3. So, I can see here the same component that here you said this was it was earlier 1.7. So, now this is this will remain as same as platykurtic data, right. So, this data is coming from a platykurtic distribution, and this is here the screenshot of the same thing. And now, let me try to show you these things on the R console, so that you can just use them very easily. So, let me try to copy this data, and before that I have to use here the command library, so that I can use this package here moments. Now, I am giving here the data time. So, you can see here the skewness of this time data is very easy to obtain, like this skewness time. And similarly, if you want to find out here the kurtosis, then you have to use the command here kurtosis, which is here 1.70. And similarly, if you consider here this missing data, so in this case I try to store the data here time dot na, you can see here time dot na, and then you can use here the this command here, where you have to give this time dot na with na dot rm equal to true. So, this now becomes a negatively skewed curve. And similarly, if you want to find out its coefficient of kurtosis, so this is kurtosis of this same options. So, this is here 1.81. So, you can see here when you are trying to base this coefficient on based on 18 observation, then the nature of the skewness has become minus. Earlier it was positive, but whereas the nature of the kurtosis, this remains the same. So, you can see here it is not very difficult to compute this coefficient of skewness and coefficient of kurtosis in the R software, but it is more important to understand what they are trying to explain you. What is skewness, what is kurtosis, and you are going to obtain them on the basis of given set of data only, right. So, now you can see here what you have learned. If you get a sample of data just by finding out the value of mean, median, mode, etc., you can get some information about the central tendency of the data. Then you have used the commands of different measures of variation, variance, standard deviation, quartile deviation, etc., and you got some idea about the nature of variability in the data. Now you have used the coefficient of skewness and you got the information whether the data has a symmetric structure around mean value or not. Similarly, using the coefficient of kurtosis, you have come to know whether the data has a hum which is more than the normal distribution sum or not. And if you try to see the magic is that you have not looked into the data. You have simply looked into this numerical values and some graphics. So this is actually the data science. When the data size is so huge, data is flowing continuously, you cannot go to the data generating process and can say how much is the data, what are those values. You cannot practically view them from your eyes because the values are so huge in numbers. In that case, this statistical method comes here, and I have given you here the idea in a univariate data set how you can measure the central tendency, variations, symmetry, peakedness using some graphical tools and some analytical tools. Now it's your turn. So today we have practically completed the data analysis for a univariate case where you have the data on only one variable. Now you know all the things. Please try to take a data set and try to apply all the tools whatever you have learned up to now, and try to dig out the information which is contained inside the data. As I told you in the beginning, the data cannot raise the hand and can say, okay, I have this mean, I have this variation, I have this type of nature, but this is only you who is going to use some tools like these tools, which some of them we have discussed here. And based on that, you are going to understand that what is the behavior of the data, what is the nature of the data, what type of information is contained inside the data, and without looking into the data. So this is what you have to learn to become a good data scientist. If you can diagnose it better, you will become a good data scientist. So with this request that you take a small data set, large data set, and try to practice all of them, whatever we have learned up to now, and try to use all the tools on the same data set so that you can get a fair idea that what these different tools are going to give different values and how they are going to be interpreted. And I will see you in the next lecture. Till then, goodbye.